Hey, welcome back to class. This is our first problem demonstrating some work that we're going to do with trusses. We'll probably be on trusses for, I would say, probably at least the next week and a half. The previous video was an introduction to chapter 6, where we talked about the characteristic of trusses. We're going to go through that and structures and frames in this chapter. Today is our first truss. I've got truss written over on the left-hand side. On these problems, we're being asked for three things. So the first thing that we're going to be asked to do is calculate the reaction forces. The second thing is to calculate the internal force in each member. And finally, we're going to be asked to determine whether the member is in tension, compression, or is a zero force member. There are two methods to do this. The method that's being demonstrated today is known as the method of joints. It's the first method that's in your textbook, and it's typically the first method shown in the textbooks that I have seen, at least. Good news is very little new arithmetic here. There's a couple of vocabulary words that we'll kind of pick up as we work through this. So for example, tension, we haven't spent a lot of time talking about tension, but tension is this idea, a member that is in tension is being pulled apart. So two force member, if the member is being pulled, it's in tension. So not to be confused with the member that's in compression, where the forces are compressing the body, pushing in the body. And then the third is the zero force member. So it is possible that there will be members in a truss where there is zero internal force. A typical question at this point kind of in our discussion would be, hey, you keep talking about this, the member. Let's kind of look over here at our picture. This truss has 5 members. Member AB, member BC, member CD, member DA, and member DB. 5 trusses. Member AB, BC, CD, DA, and BD. This question is normally followed up with, you call it member AB. Is that the same as saying member BA? And it is exactly the same. The only difference are the letters are in a different order. So I'll kind of write that over here as part of that. That way, if I get confused and I say DB and I'm looking at, and I write BD, I say DB, I've got to recognize that those are the same. In this method, and in the other method actually, the first step is to calculate the reaction forces. So we've got practice doing that. In order to save a small amount of time, rather than redraw this picture, I'm going to make a couple of erasures on it. So I'm erasing those 2 support features there. And I'm going to go ahead and draw the reactions there. Good news is in the video, you can always go back, rewind the video if you need to see that again. This is my reaction in the X direction at the smooth pin, the Y direction at the smooth pin, and the roller has a perpendicular to the plane reaction at point C. So that gives me my full free body diagram. To go about calculating the forces, first thing I would notice is, or I would start with the forces in the X direction. There are 2 of them. AX plus 6 kilonewtons. That's the force at point B. It's equal to 0, giving us that AX is equal to negative 6 kilonewtons. So as a reminder, that doesn't mean that the force is negative. It just means that I chose the incorrect direction. So since we're going to need this free body diagram, and it's so important, let me go ahead and go over and erase that arrow redraw it in the correct direction. I'll also take a minute while I'm there to write the value of AX is 6 kilonewton. Folks might say, well, Rick, you know, I could see from the picture that since the force in the B at point B was being directed to the right, it was 6 kilonewtons, and there was only one other force. That one had to be directed to the left. So I went ahead and wrote mine to the left. So if you notice that, then you are definitely encouraged to go about it that way. Well, I mean, what we have been doing, or we is me, is my next one's been force in the y direction. Looking at the free body diagram, we certainly have a AY minus 4 kilonewton plus CY is equal to 0, which really is a fancy way of saying that AY plus CY is equal to 4 kilonewton. One equation, two variables, that has been our hint that we're going to be taking a moment. I'm going to take a moment about point A. Or as a reminder, rotations that cause, oops, I didn't like that very much. Rotations that cause, or forces that cause rotations in the counterclockwise direction are considered positive. Those that cause rotations in the clockwise direction are considered negative. That's my directional diagram up there. All right, let's go pick up some stuff. So if I take the moment about point A, that makes AX and AY both non-players because they're perpendicular distance between where the force is being applied and the point that it's being applied at is 0. Now 4 kilonewtons is definitely a player. It causes a rotation about point A. It is 1 meter away from point A. CY causes rotation. CY is 6 meters away. And the 6 kilonewton force at point B causes rotation. It is 8 meters away. While you guys copy that, I'm going to kind of clean up some of that handwriting problem right there. There we go. That summation is 0. Going to pick up the directions. If I'm rotating about point A, I'm pulling down at point B. That causes a counterclockwise rotation, which is negative. Point C causes a counterclockwise, which is positive. And point B causes a clockwise, which is negative. I'll update my signs real quick. There we go. Doing the arithmetic, negative 4 kilonewtons times 1 meter is negative 4 kilonewton meters plus CY times 6 meters plus negative 48 kilonewton meters is equal to 0. Combine those terms, they're alike. Negative 4 plus negative 48 is negative 52. Add 52 kilonewtons to both sides. We get the CY times 6 meters is equal to 52 kilonewton meters. Divide both sides by 6. You end up with CY is equal to I lost my place. 8.66 kilonewtons. I'll go ahead and record that up here. 6.667 kilonewtons. That then allows us to go back into the summation of the forces in the y direction. The summation of the force in the y direction would be AY plus 8.6667 kilonewtons is equal to 4 kilonewtons. That means that AY is equal to negative 4.6667 kilonewtons. I got that by subtracting 8.667 from both sides. So 4 minus 8.667 is negative 4.667. That negative sign doesn't mean the force is negative. It just means that I have the force, my guess in the direction of the force was incorrect. I'm going to run over and change that on my free body diagram. That's very important in these problems. And while I'm over there, I'll also fill in the value, 4.6667 kilonewtons. And so that gives us all the reaction forces. Now, as we work through the videos, one of the limitations that I currently have is I only have the one whiteboard. So at a point in the video, after we get done with some work, I'm going to erase some things. In this particular case, I'm about to erase the middle calculations and the direction of the moment at each of the points. The good news is, if you needed to go back and look at the, what we've done up to this point, you'd be able to stop the video here, go backwards or rewind the video and rewatch it. So the information, the historical information is still there. It just won't be on the board moving forward. We're not going to need that. I'll keep the values for CY, AX, and AY because we're going to need that in our calculations. All right. So our first responsibility was to calculate the reaction forces. We've done that. I'll put a check mark there. Our next thing is to calculate the internal force of each member. All right. So as part of the instruction, I was talking to you about, how to label the members. I'm going to keep that up there. I'm going to use that as a table. And every time I get an internal force, I'm going to write that up there. Help me keep track. The method that we use, the method is called the method of joints. That means that we're going to go joint by joint. And as we go joint by joint, we're going to choose a joint each time. Choose a joint with, I don't want to say that. I'll say with 2 or fewer unknown member forces. We're going to be looking for joints that have 2 or fewer unknown forces, internal forces. Draw a free body diagram of that joint. And then use the equilibrium equations to calculate the internal force of the members at the joint. That's our plan of attack. So we're going to, in the method of joints, you go from joint to joint, looking for a joint with 2 or fewer unknown member forces, draw a free body diagram of that joint, and then use the equilibrium equations to calculate the internal forces of the members at the joint. You can start at any joint that you want. So in the truss that we're working with, you could start at joint A, for example. You could start at A. If I started at joint A, it has 2 unknown member forces. I don't know what the force is in AB, and we don't know what the force is in AD. I could not start at joint D. In joint D, there are 3 unknown member forces, DA, DB, and DC. would not be able to start there. Joint B would not be able to start at joint B either. There are 3 unknown member forces at joint B: BA, BD, and BC. Could start at joint C. There are 2 unknown forces at joint C: CD and CB. So our choices are joint A or joint C. I'm going to start at joint C. There's because I want to teach a vocabulary word that's in joint C. All right, drawing a free body diagram of joint C. We already know that there's a force CY. That was the reaction force to those beautifully drawn rollers that I had up there earlier. CY, which was 8.6667 kilonewtons. There is some force CD, and there is a third force CB. I want everyone to look at joint C in the free body diagram. I'm looking at the free body diagram. I'm seeing there's an upward force CY being applied at joint C. My intuition tells me that if the truss is at equilibrium, then each joint is at equilibrium. And if there's only one force being applied in the upward direction, then force CB is going to be in the downward direction. We have talked quite a few times in class about how do you know whether to pick it, how do you know whether to pick it in the upward direction, downward direction? I say, hey, just take a guess. I'm taking an educated guess right here that BC is in the downward direction, in the downward direction. All right, using the equilibrium equations, equilibrium or the summation of forces in the x direction. There is only one force in the x direction, and that's the force in member CD. So CD is equal to 0. We would call member CD a 0 force member. There is no force internal to member CD. Wouldn't matter whether I had the force being directed from right to left or left to right. There's only one force in the x direction. The summation of those forces is 0. So the force in member CD, or is also is referred to as DC, is equal to 0. So I'll fill that into our table. I'm also going to put a check mark here so that I know that one's done. All right. Summation of the forces in the y direction. Let's see, we've got CY, 8.6667 kilonewtons being applied upwards, minus BC. BC was being applied back, downwards. If we do the arithmetic, that gives us that BC is equal to 8.6667 kilonewtons being applied downward. All right, next vocabulary word or next fact. A force that is going away from a joint is tension. Tension. A force going away from a joint is tension. A force going toward a joint is considered compression. So I'm going to try to write it over here. I'm going to use T for tension and C for compression. Okay. A force going away from a joint, force going away from a joint is considered to be in tension. A force going toward a joint is considered to be in compression because it is a reaction to what's going on to the member. So that tells me, I'm looking at BC here. The arrow shows that we have the forces going toward the joint. So when we go over here to the scorecard and we write down that BC is equal to 8.6667 kilonewtons, we also have to indicate that it is in compression. Now, a typical question would be, so I'm going to redo this problem very quickly. There's point C, there's CY. For some reason, I write BC going away. CY is still 8.6667 kilonewtons. BC I have shown going away. If I do the equilibrium equation for Y in this free body diagram, I would get 8.6667 plus BC is equal to 0. Subtract 8.6667 from both sides. We would have calculated BC is equal to negative 8.6667 kilonewtons. The negative would not say that the force is negative. It would just indicate that I have the arrow drawn in the wrong way. It should have been drawn going downwards, which now says that because I now have, which would now be an indication the force is going toward the joint, so the member is in compression. The member is in compression. So now we now have BC, so we are 3/5 of the way in. Let me erase the board. While I erase the board, I'm going to talk for a couple minutes. So I get that identifying whether a member is in tension or compression can be difficult. The best thing that I have for you right now is these two little hints. That if we show a force, if a force is going away from the joint, we say that the member is in tension, and a force going toward a joint, the member is in compression. I would write that down in my notebook, and I would have that out as I work the problems. And then we'll hopefully develop some intuition or a better sense of why that is as we go through the problems that we have. All right, we're heading down. So point D. I'm at a point, we are now at a point where we can look at point D. So point D has, I think we talked about this already, had member DA, which we didn't know, member DB, which we didn't know. We know DC now, and we're given the 4 kilonewtons there. So we're at a point where we can hopefully fairly quickly calculate what's going on at point D. Now we said, so let's see, there's CD, there's DB, and there's AD. DB, DC, which is a 0 force member. I mean, essentially it's not even there. I'll write 0. And then DA. I'm seeing that we got some stuff going on here. So D, I wrote the B upside down. DB is at a diagonal. I'm just going to go down here real quick and see what we got going on. I mean, we're going to need the angle for that. We're going to need, the X and Y component for that. So we'll grab that while we're here. So that's DB. 8 and 5. So this is 8 meters here, 5 meters here. Inverse tan of 8 over 5 gives us that angle of 57.99. degrees. So 57.99 degrees. I'm going to draw the triangle again. I'll show you why. dB is here. So if this is theta, that makes in our force triangle, this would be dB cosine 57.99, and this would be dB sine 57.99. That might keep our free body diagram a little less crowded. Okay, I'm ready. A couple things I noticed right away. Summation of the forces in the x direction is equal to dA plus 0, which was dC, plus dB cosine 57.99 degrees. That summation is equal to 0. That doesn't help us because that gives us two unknowns here. So we might be stuck looking at in the y direction. Summation of force in the y direction, -4 kilonewtons plus dB sine 57.99. We could definitely solve for dB. So dB is equal to, let's see, so dB sine 57.99 is equal to 4 kilonewtons. Divide both sides by sine of 57.99. dB is equal to 4 kilonewtons divided by sine 57.99. And that gives us a value of 4.7172 kilonewtons for dB. It is positive, which says that I have the arrow in the correct direction. Force dB is going away from joint D, which means that dB is in tension. 4.7172 kilonewtons in tension. Since we have that, since we know what the value of dB is, we can go back into summation of forces in the x direction. The summation of forces in the x direction is equal to dA. I'm not going to rewrite the 0. Plus 4.7172 kilonewtons times the cosine of 57.99 is equal to 0. 4.7172 times cosine of 57.99, I think is 2.5. It was earlier today when I practiced anyway. Kilonewtons, which means that dA is equal to negative 2.5 kilonewtons. That means that I have the arrow drawn incorrectly for dA. It means I have the arrow drawn incorrectly for dA. What I should have had, let me draw it over here, dB. I'm not even going to put dC there because it's 0. 4 kilonewtons. I should have had it drawn this way, which means the arrow is going toward the joint, which means dA is in compression, Again, I completely understand that the compression and tension thing can be a little confusing. My hope is as we move on through the chapter, we develop a better instinct for that. We're down to one left. So we have dB and dA. Right, give me a minute. hopefully not a whole minute, but give me a second to erase. I was thinking we might need this. Kind of got freaked out a little bit. I was erasing for no reason. A lot quicker to erase on our dry erase board in the classroom, that's for sure. All right. We are down to one joint left. Good old joint A. Joint A. So we've got joint A. We have a member AB coming off of joint A. Now joint A, or joint AD was in compression. That was the one that we just did. So if it was in compression at point D, it is also in compression at point A. So DA will be drawn going into point A. We've got AY. We know that direction is correct. Remember, I got it wrong earlier. I had to go back and fix that. I had AX also incorrect. 6 kilonewtons. I think AD was 2. I have a mistake in our chart here. It should have been 2.5 kilonewtons. I apologize for that. That's 2.5. All right. We're going to probably need this angle. So this angle can be calculated. Let's go down here real quick and look at it. 8 meters, AB, 6 meters on the bottom. So inverse tan of 8 over 6 is equal to, that's theta. Theta is inverse tan of 8 over 6. If we do the arithmetic for 8 over 6, I think it comes out to be, it's one of our friendly ones. I think it comes out to be 53.13. 53.13 degrees. So as a reminder what that means, 53.13 AB. The x component would be AB cosine 53.13. Y component AB sine 53.13. That should set us up. Summation in the it doesn't really matter. We'll use the Y one. It looks like there's a little bit less arithmetic involved. Summation of the forces in the Y direction, negative 4.6667 kilonewtons plus AB sine 53.13 degrees is equal to 0. Add 4.667 to both sides. We get that AB sine 53.13 is equal to 4.66667 kilonewtons. Divide both sides by sine 53.13. And that gives us a value for AB. Let me double check it. I can't read my handwriting. 4.667 divided by sine 53.13. Yep, 5.8333. So AB, force AB is, or the force in member AB is 5.33 kilonewtons. It is it came out positive, which means I was a good guesser on the direction of AB. AB is pulling away from the joint, which indicates that the internal force is in tension. 5.333 kilonewtons in tension. So we have calculated the reaction forces. We've calculated the internal force in all 5 of the members, and we've determined whether each member was either in tension, compression, or is a zero force member. Again, I acknowledge the tension compression part can be a little bit confusing, but I also have seen historically that it gets easier the more problems that we do. So I'm going to take a supper break. I'll come back, hopefully to videotape a second problem for us. Hope you're having a great day. See you soon.